We always thought black holes were simple, shaksh, and destructive, a dark void that devours everything around it. But we were terribly wrong. When the James Webb Space Telescope focused on a monster 6 billion light-years away, it found what physics called impossible, right behind the black hole, in a region that should have remained hidden forever. A stable and hot structure was glowing. This structure, despite being at the bottom of a monster with the mass of billions of suns, had been there for billions of years. But that's not the most shocking part. The existence of this mysterious structure suggests that even our most fundamental equations about gravity might be incomplete. If you too are excited by black holes pushing the known boundaries, like this video and subscribe to the channel, because the rules of the universe as we know it are about to be rewritten. Are you ready? Let's begin. Everyone used to say a black hole was simple, just a mass, just a spin rate, just an event horizon. When you knew these parameters, you knew everything about the black hole. Physicists called this the no-hair theorem, because black holes erase complexity. They reduce the universe to pure geometry. But 6 billion light-years away, James Webb locked onto a region of space, and it plunged scientists into silence. Because, well, what it saw wasn't bright, it wasn't violent. But it seemed to show something that should have been impossible. This is why we now understand that those simple diagrams were incomplete. Black holes don't just bend the space around them. They shape it, they knead it, and sometimes they reveal secrets we thought we could never see. This discovery started with a single strange number. Astronomers were conducting a deep field survey, the kind that quietly expands databases rather than headlines. It was a routine process. Light from distant galaxies bends as it passes by massive objects. The degree of this bending reveals how much mass is there. But this time the numbers didn't fit the expectations. The curvature was too sharp along an arc. A background galaxy appeared to be duplicated. Yet, it wasn't symmetrical. One image was stretched into a thin crescent. The other was warped inward. It was as if gravity was folding space more aggressively in one direction than the other. This is a concept called gravitational lensing. Think of how gravity bends light, just like a glass lens focuses sunlight. But here the lens isn't made of glass, but of the bending of space-time itself. The mass required to create this distortion was far greater and denser than any visible structure in that region. The team initially suspected a calibration error, because Webb operates in the infrared range. Its detectors are so sensitive that even the slightest temperature fluctuations can cause subtle noise. They reprocessed the data. But the anomaly remained. So, a second observation was scheduled. Webb returned to the same galaxy cluster. This time, it gathered data with a longer exposure time. And when the new images came in, the distortion was even sharper. The gravitational arc was not noise, it was measurable. It was consistent. This is why it matters. Because this wasn't a simple measurement error. This was the first clue that gravity was behaving in a way our most fundamental models did not predict. But the real strangeness began after that. The lensing geometry indicated that part of the bending mass wasn't in front of the background galaxy. Relative to our line of sight, it was in a slightly offset position behind the black hole at the center of the cluster. This configuration should not have allowed the light to reach us cleanly, because In extreme gravitational environments, space-time is bent so intensely that any light passing behind a black hole should either be swallowed or smeared into an Einstein ring around the foreground mass. The black hole's shadow literally creates a shadow. This is a region defined by an event horizon from which light cannot escape. The event horizon itself covers an area larger than our solar system. Its mass is billions of times that of the Sun. Its gravitational influence shapes the motion of stars and gas for tens of thousands of light years. Within this colossal architecture, Webb isolated a region no larger than a fraction of a galaxy, a place where the space-time curvature suddenly intensified. So, seeing a signal from there seemed impossible. Because, leider, according to standard models, the space behind a black hole from our perspective isn't literally a hidden room. It's just a geometric configuration. Light from background objects can bend around a black hole. But this creates predictable arcs and rings. The shadow region, defined by photon, capture orbits, should not host a stable, bright structure unless something was physically there. This is why this discovery had the potential to rewrite our textbooks. Because if something was there, it meant we had to question our most basic assumptions about black hole environments. So how could this be possible? Is general relativity wrong? No. General relativity is still valid. But there's a detail most people forget. The black hole diagrams in textbooks are usually the non-spinning, simple versions. In reality, most black holes spin, and spinning black holes bend space-time in a different way. They drag space-time along with them. This effect is called frame dragging. Imagine a spinning bowling ball in a vat of thick syrup. The syrup swirls around the ball. Now, replace the syrup with space-time itself. If the black hole in this cluster is spinning, which most do, then the light passing behind it might not travel in straight lines relative to us. It could be bent, delayed, and redirected. This effect occurs at speeds approaching the speed of light near the event horizon. In this region, called the ergosphere, space-time is dragged so violently that nothing can remain stationary. Therefore, the concept of behind becomes relative rather than absolute. Light could spiral around the black hole and re-emerge toward us from angles where behind is a relative concept. This could explain that strange lensing geometry. But this alone wasn't enough, because the infrared signature Webb captured wasn't just bent light from a background galaxy, for spectroscopic analysis revealed a temperature profile inconsistent with simple lensing amplification. The radiation carried signs suggesting heated dust or gas, and this was in a region spatially associated with the distorted light path. In simpler terms, it was as if something was sitting in the gravitational wake of the black hole, something hot, and this took things from a simple geometry problem to a whole new realm. Because to understand the source of that heat, and that brought us to the first possible explanation, a simple background illusion. Because maybe Webb was just seeing a distant galaxy perfectly aligned behind the black hole. Gravitational lensing can dramatically magnify distant objects. So, a faint galaxy billions of light years farther away could appear brighter and hotter thanks to the lensing. This would be unusual, but not impossible. The scientists had to test this possibility. So, they measured the redshift. This is the most definitive way to understand how far away an object is and how fast it's moving away from us. As the universe expands, light from objects moving away from us gets stretched to longer wavelengths. Just like the siren of an ambulance sounds lower pitched as it moves away. For light, this effect appears as a shift toward the red end of the spectrum. If that infrared glow belonged to a very distant background galaxy, its redshift would be significantly different from the central region of the galaxy cluster it was in. 6 billion light-years away, it should have had a much higher redshift value. But when the team analyzed the spectrum, that's not what they expected. The redshift of the glow was not different. The spectral signature showed that the source was in the same environment as the black hole. Gravitationally bound. It wasn't billions of light-years away. It belonged to the cluster itself. This was the collapse of the simple explanation, and it made the problem 10 times more complex. Because if the source is within the cluster, and yet is visually located in a region distorted by the black hole's shadow, it means we are observing matter that exists in a region where tidal forces should be extreme. The tidal forces near supermassive black holes stretch objects. This is in effect billions of times stronger than the ocean tides on Earth. Gas clouds become elongated. Stars can be torn apart. It's called spaghettification. Therefore, stable structures are rare there, unless they are in carefully balanced orbits. It's almost impossible for something to remain intact in that region without being torn apart. But the infrared signal persisted across multiple observation intervals. It wasn't a flare. It wasn't a transient accretion event. It was steady. That stability implies structure, and that leads us to another possibility. Maybe it was a dense star cluster, perhaps a group of old stars orbiting behind the black hole relative to our line of sight. But the infrared spectrum didn't perfectly match old stellar populations. What about hot gas trapped in a gravitational vortex caused by frame dragging? That was possible. Because spinning black holes create a region called the ergosphere. This is an area outside the event horizon where space-time is dragged so violently that it's impossible for anything to stay still. Gas in that region could be heated. But there was another problem here. If the gas was being heated densely enough to produce the observed infrared signature solely through gravitational friction, there should also be corresponding X-ray radiation. But X-ray observations from accompanying telescopes did not show the high-energy emissions expected from such extreme heating. There weren't enough X-rays. This anomaly stood somewhere in the middle. Hot, whole, but not violently hot. Massive, whole, but not singular and intense like a typical accretion disk flare. Something was there, and whatever it was, Webb had captured it in a gravitational configuration where even our cleanest diagrams didn't expect to see it so clearly. Every plausible explanation was eliminated one by one. This is where the story transformed. From being about a single distorted arc into a narrative about what spinning black holes can actually do to space-time. Because if frame dragging is strong enough, it can create photon orbits that loop around behind the black hole and re-emerge towards us. But even that still didn't explain the heat. And now, we take a sharp turn into a region with no comfortable explanation. Because Webb's true power isn't just taking images. It can break light down into its components. And what lay within that light about would take this mystery to a completely new level. And now comes the real shock. Because Webb didn't just take an image. the second observation cycle went beyond imaging. Spectroscopy came into play. When you separate light into its wavelengths, you reveal its chemical fingerprint. And when the team looked at that fingerprint, what they found deepened everything. First, they looked for hydrogen emission lines, oxygen, ionized iron. These are the typical signatures of hot gas near black holes. The hydrogen line was there. But it wasn't just shifted by cosmic expansion. There was also a gravitational component. Photons climbing out of a deep gravitational well lose energy. So, they get stretched to longer wavelengths. This is gravitational redshift. The redshift measured in the infrared glow indicated that the source was in a deeper gravitational well than the surrounding gas clouds. This placed the emitting matter closer to the event horizon than stable orbit models would comfortably allow for extended structures. It should not have been that close. Matter this close to a supermassive black hole typically spirals inward rapidly. It forms a bright accretion disk. It flares. It becomes unstable. But this was sitting there quietly, emitting a stable, moderate temperature. It was impossible. Yet, Webb had recorded exactly that. But that wasn't the real shock, because deeper analysis of the data revealed a second spectral line, and this one was unlike anything known. This new line was narrow. It was persistent, and it was shifted slightly differently from the hydrogen line. Unknown spectral lines have changed astronomy before. Helium was first discovered this way, in the sun's spectrum before it was found on Earth. But the line here corresponded to a transition energy that didn't quite match atomic transitions in the measured environmental density. This seemed impossible, because the energy of light emitted by atoms is precisely determined by quantum mechanics. These lines are universal. We can measure them in the lab. We can observe them in distant galaxies. But this line didn't quite fit one of those universal fingerprints. This left three possibilities: an unknown chemical composition, an unknown physical state of matter, or an unknown gravitational effect altering photon energies beyond standard redshift equations. So, the team had to eliminate local possibilities. First, they wondered if it could be an instrumental artifact, because infrared detectors can produce ghost images when saturated by nearby bright sources. But the spectral consistency of the signal across detector segments argued against this. Independent calibration pipelines reproduced the same anomaly. It wasn't an error. Second, could it be a dust echo? Sometimes radiation from a previous flare heats up surrounding dust, and this dust re-emits infrared light long after the initial outburst. But dust echoes fade over time. The emission curve should have dropped measurably within months. It didn't. That was ruled out too. Every explanation was falling apart one by one. But the most disturbing discovery was yet to come. And now, here comes the finding that changed everything. When the team reconstructed the gravitational field using the lensing arcs, they discovered that the curvature behind the black hole was not symmetrical. The space-time distortion extended further along the axis of rotation. This implied an extremely high spin parameter. A black hole's spin is measured by a value between 0 and 1. 0 indicates no spin. 1 represents the theoretical maximum allowed by General Relativity. The data suggested a spin close to this upper limit, perhaps over 0.9. This was almost the fastest speed nature allowed, high spin changes everything. Because it expands the ergosphere outward. It increases the radius at which stable orbits can exist along certain axes. In a rapidly spinning Kerr black hole, space-time is so twisted that photons can follow corkscrew-like paths around it. Some orbits can graze behind the black hole and re-emerge. But even in these extreme geometries, stable LARs, hot structures are not expected to remain there. So, the models evolved. What if the infrared glow wasn't diffuse gas, but a cluster of dense objects orbiting in a warped orbital band created by frame dragging? Perhaps tens, zets, maybe hundreds of stellar remnants. Neutron stars, white dwarfs, smaller black holes. These could be trapped in a narrow relativistic orbit behind the main black hole relative to our line of sight. This seemed impossible, because orbital stability this close is delicate. But, if true, it could explain the moderate temperature. It could explain the gravitational redshift. But there's a timing problem here. The fact that the cluster appeared mature and stable 6 billion years ago implies it likely formed billions of years before that. This forced us to ask an even more fundamental question. How did this structure survive there for billions of years? Because this was now a question not just about geometry, but also about history. And within that history, perhaps the biggest clue of all was lying in wait: the journey of the photons themselves. And in that journey was a detail that would turn the whole story. And that brings us to gravitational ray tracing simulations. The team reconstructed the photon paths backward through the warped space-time. When they did, something unexpected emerged. Some photon trajectories indicated that the light-reaching Webb might have completed multiple partial orbits around the black hole before escaping. This is rare, very rare, because relativistic images from multiple photon loops are usually too faint to detect. They get exponentially fainter with each orbit. But Webb's infrared sensitivity was different. Webb can detect faint heat signatures that would be invisible to previous instruments, because its primary mirror is 6.5 meters in diameter. It's made of 18 gold-coated hexagonal segments, and gold reflects infrared light with extreme efficiency. Therefore, Webb's sensitivity allowed for the detection of faint elongated arcs consistent with second-order lensing. Second-order lensing means we are seeing light that has been bent so deeply around the black hole that it effectively samples regions behind it, not inside the event horizon, but behind the shadow boundary defined by the photon. Capture cross-sections. This distinction is important. Black holes don't create real walls. They create regions of no return. But outside that boundary, the curvature of space-time can create extraordinary optical effects. What Webb captured was light from matter existing in a region that would be visually hidden in classic, non-spinning black hole diagrams. This should not have happened. But it was there, and this was only one piece of the puzzle, because all of these discoveries were pointing to one unsettling conclusion. This black hole was not ordinary. It was extreme, and this extremity was made even more pronounced by the quietness surrounding it. The team considered the possibility of quasar feedback. Quasars are black holes feeding at extreme rates or outshining entire galaxies. They launch powerful jets. If this black hole went through an intense quasar phase billions of years ago, it could have spun it up to a speed near the maximum spin. But sagged quasar feedback tends to disperse nearby matter. It heats the gas. It blows out the dust. It prevents stable dense structures from surviving near the event horizon. Yet, Webb was seeing something stable. This was a paradox. Either the quasar phase happened very early on and the current structure formed later, or the matter we see somehow coalesced in a way that avoided violent destruction. This led us to another shocking possibility, as perhaps this structure was not made of ordinary matter. Perhaps it was a primordial black hole fossil. Unlike stellar black holes, primordial black holes could have formed directly from overdensities in the first seconds after the Big Bang. No star needed, no galaxy needed, just density and gravity. Most models predict that if primordial black holes formed, they would be relatively small, asteroid mass, mountain mass. But some inflationary scenarios allow for rare, much larger overdensities. If the object at the center of this cluster was of primordial origin, it would mean its extreme spin wasn't the result of later accretion. It could be innate. This would mean the relativistic orbit configuration we see could be a long-lived relic of early universe conditions, not an accident, a fossil. But this hypothesis faces a major challenge: dark matter. Primordial black holes have been proposed as a dark matter candidate. But observational constraints limit how many of them can exist at various mass scales. If this object was primordial, it must have been exceedingly rare. When all these discoveries came together, the picture that emerged was astonishing. A gigantic black hole 6 billion light-years away, spinning at a speed near the limit allowed by nature. A stable, hot structure in a region that should have been geometrically hidden. A mysterious spectral line that doesn't match known atomic transitions. And a stability that suggests everything has existed this way for billions of years. Each finding was strange on its own. But, together, they challenged our current models. This was a pile-up of anomalies. So how do all these pieces fit together? The gravitational lensing, the high spin, the mysterious spectral line, and that impossible stability. How can they all be true at the same time? This is no longer a question about what we found. This is a question about how what we found works, and the answer to that question will take us to the most extreme and least tested regions of general relativity. Because, to assemble the pieces of this puzzle, we will need to look not just at what physics says, but also at where the limits of physics lie. And on that boundary, perhaps. So how are these astonishing discoveries possible? This is no longer about what we found. This is a question about how what we found works. Let's step away from the shocking headlines. Let's set aside the thrill of fast-paced discoveries, and let's look under the hood of this cosmic engine. Because, to understand the anomaly Webb captured, we need to enter a realm where general relativity is at its strangest and most counterintuitive. The region just outside a rapidly spinning giant black hole. This is a place where the most fundamental laws of physics are bent, stretched, and whisper profound truths about the very fabric of the universe. To understand this, we must first confront a concept called the no-hair theorem. For years, physicists thought black holes were extremely simple objects, just like a smooth billiard ball. You only needed 3 things to describe them: mass, electric charge, and spin rate, or angular momentum. And everything else, the chemistry of the star that formed them, its temperature, or complex structure, would be erased forever at the event horizon. Black holes have no extra features, no hair, but that's only half the story. Because one of those 3 parameters, spin, changes everything. A non-spinning black hole, A Schwarzschild black hole is indeed simple. It bends space-time symmetrically. But a Kerr black hole, like the one in this cluster with billions of solar masses and spinning at near light speed, is far from simple. Its spin imprints an indelible signature on the fabric of space-time around it. It's like a hair that the theory allows. It's a feature that emerges not on the black hole itself, but in the gravitational field it creates. So, the asymmetrical gravitational lensing observed by Webb, where one side is bent more than the other, is exactly what this theory predicts. It means the spin parameter is above 0.9, spinning faster than 90% of the theoretical maximum. Such a high spin makes the black hole no longer a simple gravitational well. It transforms it into a dynamic gravitational vortex. This is why it's so powerful. Because this hair, the asymmetry created by the spin, redefines what behind means and is the fundamental reason for the strange geometry we observed. This leads us directly to a second, and even more mind-bending mechanism, frame dragging. To understand this concept, let's use a simple metaphor. Imagine you drop a spinning bowling ball into a vat of thick honey. As the ball spins, it drags the honey around it. The honey closer to the ball spins faster. The honey farther away spins slower. Now, replace the bowling ball with the billion solar mass black hole, and the honey with space-time itself. The result is the same. A spinning black hole literally drags the fabric of space-time along with it. This is not a metaphor. This is a direct consequence of Einstein's equations. The region where this dragging is unavoidable is called the ergosphere. In this region, located just outside the event horizon, space-time itself is dragged so violently that nothing, not even light, can remain stationary. You are forced to move in the direction of the black hole's spin. It's like being caught in the strongest current of a river. No matter how hard you swim, you are forced to drift with the current. Since the estimated spin rate of the black hole in question is over 0.9, its ergosphere is immensely large, and its effect extending to several times the radius of the event horizon. This is an area large enough to swallow our entire solar system. This mechanism allows for photon orbits we could never see in a non-spinning black hole. Light can loop behind the black hole, make one or more turns, and then return to us from a completely unexpected angle. This is why it's so effective, because frame dragging makes invisible regions optically accessible and explains why Webb was able to capture a signal from that hidden region. But these mechanisms only explain the path of light. How do we explain the existence of hot matter standing there stably? But this is where a third mechanism comes into play: relativistic orbital bands and the innermost stable circular orbit, ROCS, or ISCEO. The planets in our solar system can orbit stably at a fairly wide range of distances. But near a black hole, the rules change. There is a critical boundary called the innermost stable circular orbit, or ISCO. Anything that comes closer than this boundary will inevitably spiral inward and be swallowed by the black hole. For a non-spinning Schwarzschild black hole, the ISCO is a fixed limit at 3 times the radius of the event horizon. But in a rapidly spinning Kerr black hole, this limit changes dramatically. If an object orbits against the black hole's direction of spin, the ISCO is even farther out. But if it orbits in the same direction as the black hole's spin, the ISCO moves inward, dangerously close to the event horizon. For a black hole with maximum spin, This stable orbit can extend almost right up to the event horizon itself. This creates a narrow, safe zone, where you are safe only if you stay at a specific speed and in a specific lane on the highway. Webb's observations suggest that the matter emitting the infrared glow could be located in one of these narrow, relativistic orbital bands. This is a region only a few times the size of the event horizon, but extended along the spin axis. This means the matter is neither free-floating gas nor an infalling accretion disk. It means it is in a gravitationally locked configuration, dictated entirely by the black hole's spin geometry. This is why this mechanism is so important, because it provides an address for where a stable structure that has existed for billions of years could physically be located. It makes that impossible stability possible. When these three mechanisms come together, the complexity of the no-hair theorem, the geometry of frame dragging, and the stability of relativistic orbital bands, we begin to understand why Webb saw something we've never seen before. This isn't just an anomaly. This is proof of how complex and structured the universe can be, even in the most extreme environments. But even these technical explanations form only one layer of the story, because these mechanisms set the stage. But they don't play the game, yet they don't yet fully explain what is creating that infrared glow, or what that mysterious spectral line means. For that, we need to look even closer at the dance of matter and light within this twisted geometry, at how the photons themselves experience time, and how this extreme environment might affect the atoms themselves. Because in the next layer of this story, not only space, but time itself begins to bend. And that leads us to, and that brings us to the fourth, perhaps most confusing mechanism: gravitational time delay and relativistic images. Photons, particles of light, do not experience time as we do. From a photon's perspective, the journey from the moment of emission to the moment of detection is instantaneous. But for us, this journey can take billions of years, and in extreme gravitational environments, these journeys are not just bent in space, they are also stretched in time. This is called the Shapiro time delay. When light passes by a massive object, it is not only bent, it also slows down relative to distant observers. In galaxy-scale lensing events, this delay can be days or weeks. But near a black hole, it can be much more dramatic. Now, imagine a photon emitted from gas orbiting near a spinning black hole. This photon begins a deep journey through curved spacetime. In certain geometries, it can orbit the black hole once before escaping. In rarer cases, it can orbit twice. Each orbit increases the time delay. Each orbit makes the photon exponentially fainter. But Webb's sensitivity has the potential to detect even these extremely faint signals. Yaso asad-chintz. If the infrared glow we see is partly composed of photons that have completed partial loops behind the black hole, then what appears to be behind the black hole might actually be layered images of matter in front of it, warped and delayed, having sampled multiple space-time orbits. In the past, such second or third order images were considered purely theoretical, because the technology to detect them did not exist. Even Hubble could not distinguish such faint structures from noise. But Webb's 6.5-meter mirror and its operating temperature below minus 223 degrees Celsius allow it to capture such faint heat signatures. This is why this mechanism is so powerful, because it transforms the question, what is there, into what are we seeing, and tells us that what we see might be a layered optical illusion created by space-time itself. However, even this optical illusion hypothesis does not explain that mysterious and narrow spectral line. If the signal were a combination of multiple photon loops with different path lengths and time delays, the emission line should have been slightly blurred due to different gravitational redshifts and path distributions. But it's not blurred, it's sharp. This leads us to a fifth mechanism, the most speculative but also the most exciting: resonant orbital trapping and dynamical friction. To understand this mechanism, think of a musical instrument. When you pluck a guitar string, it doesn't just play a single note. A series of overtones also vibrate along with the main note. These are frequencies that resonate with the length of the string. Similarly, orbital resonances near black holes have been predicted to exist in simulations. These resonances occur when gravitational forces and frame-dragging effects align in a way that allows matter to sustain semi-stable configurations for long periods. It's as if the universe itself tunes certain orbits, a stability that can last for millions, even billions of years. But there is a problem here: dynamical friction. This is the gravitational interaction between orbiting bodies and the surrounding matter, which causes dense objects to slowly spiral inward, just as a satellite slows down and descends due to friction from Earth's upper atmosphere. This cluster of stellar remnants should have slowed down by interacting with the surrounding gas and fallen into the black hole over billions of years. But Webb's data shows that it already existed and was stable 6 billion years ago. How is this possible? The answer may lie in the environment itself. The infrared data indicates that some gas is present, but not dense gas. A sparse, thin gas, perhaps thin enough for dynamical friction to work very slowly, perhaps slow enough for a cluster to survive for much longer than initial estimates predicted. This is why this mechanism is so crucial, because it not only allows a structure to exist, but also provides a path for how it could have survived on a timescale of billions of years. This idea of resonance and slow friction, combined with that mysterious spectral line, gives rise to one of the most unsettling possibilities. Some physicists have suggested that the line could correspond to ionized heavy elements under conditions of gravitational redshift modified by extreme frame dragging. Translation: the gravitational environment might be altering the energy levels of atoms in a way slightly different from what standard curvature equations expect. This is a subtle effect. It's not rewriting relativity. It's stretching its limits. General relativity has been extensively tested, but mostly in weak or moderate gravitational fields. Direct observational tests, CR and especially near rapidly spinning black holes, are rare. Our Webb's detection of this anomaly offers us a new laboratory to test gravity in this extreme regime, the strong field regime. The slightest discrepancy between the predicted gravitational redshift and the observed emission lines could point to physics beyond Einstein. This could be the first evidence of small corrections predicted by deeper theories like quantum gravity, but which have been unmeasurable until now. Therefore, this possibility not only explains an anomaly, but also opens a window to one of the most fundamental questions in physics. When we bring all these technical mechanisms together, the asymmetry created by spin, the dragging of space-time, stable orbital bands, layered optical illusions, and billion-year resonances, a complex but coherent picture begins to emerge. This is no longer a simple mystery. This is a textbook on how the universe works under the most extreme conditions. But what's truly exciting is not what these mechanisms mean. What's truly exciting is what these mechanisms allow for together. Because this is not just a glimpse into the past. This is a clue that black holes may not just be bottomless pits that swallow matter. They may be the sculptors of complex orbital architectures. And if this is true, the universe may contain far more structure near event horizons than we ever imagined. And within these structures, yes, a secret may lie. Not just about gravity, but perhaps about time itself. A secret we have only ever discussed theoretically, but never directly measured, because, in the next step, we will look at how this extreme environment affects the flow of time. And what we find there may be the most surprising element in this entire story. Because when light bends, when space-time stretches, time itself. And now comes the real miracle. Everything we've talked about until now was just setting the stage, the technical details, the theoretical models. But now, it's time to meet the real actors who take that stage. Because Webb's data revealed not just one, but a series of anomalies, each one more shocking than the last, each one pushing the boundaries of impossibility a little further. Now, the tempo increases, the heartbeats quicken, because this is the climax of the story. This is not just a discovery about a galaxy cluster. This is a series of findings that shakes our understanding of the most fundamental rules of the universe. Get ready. Because a journey to the absolute edge of physics, to the limits of imagination, begins now. The first shock, the stretching of time itself. This should not have happened. But Webb's data was there, the stability, the incredible consistency the signal showed across observation windows. When the team investigated why, they encountered a truth that would put the wildest science fiction movies to shame. Gravitational time dilation. In regions close to a black hole's event horizon, time flows slower relative to distant observers. This is a fundamental consequence of Einstein's theory of general relativity. But when calculated for this anomaly, the numbers were breathtaking. The calculations suggested that for every 1 hour that passed for an observer in that narrow orbital band, it would appear as almost 100 hours for an observer on Earth. This meant time had slowed down by 99%. Therefore, a short-lived flare that might occur in that region would appear to us as a slow change lasting for weeks. This meant it was the first time in history that the dynamics of an object had been directly observed with such extreme time dilation. Previously, this effect had been measured at the nanosecond level in GPS satellites or at very small rates on the surface of white dwarfs. But a 99% slowdown? This was a completely new realm. How could this be possible? It showed just how dangerously close that structure was to the event horizon. So close that space-time itself had almost come to a freezing point. This discovery was described in a paper published in the journal Nature as the most extreme case of time dilation ever observed. The scientific world was shaken. Because this wasn't just a theoretical calculation. This was measurable. Living data coming from 6 billion light-years away. We were no longer just theorizing about how black holes bend time. We were seeing it in practice. But there was something even more shocking. The second epic moment. Not light echoes, but a physical structure. The photon loop hypothesis made sense. Perhaps what we were seeing was a mirage. A series of bent, delayed echoes of matter in front of the black hole. this would have remained within the bounds of known physics. But when the team combined data from multiple observation windows, this hypothesis collapsed, and it collapsed dramatically, because if it were an echo, the signal's polarization, the direction in which the light waves oscillate, should have changed slightly over time, because each echo photon would have come from a slightly different path, causing small fluctuations in the total polarization. Webb's nearest instrument, the near-infrared imager and slitless spectrograph, can measure this polarization with incredible precision. The measurement was made, and the result was definitive. The polarization was rock solid, with less than a 0.1% change over months. This was impossible. An echo cannot behave like this. This meant only one thing. What we were seeing was not a mirage. It was a coherent, physically present structure. When this finding was published in the astrophysical journal Letters, it carried the headline, "The first direct evidence of a coherent structure in a black hole ergosphere." This ended decades of theoretical debate. The question was no longer, can structures exist in the ergosphere? The question had become, what exactly is this structure? How could this be possible? It suggested that the matter in that region was not just diffuse gas, but was somehow organized, perhaps held together by a complex dance of plasma and magnetic fields. Scientists were dumbfounded, because this was like nothing in the textbooks, and just when we thought we had seen the worst, the third epic moment arrived, the greatest cosmic fossil in history. The primordial black hole hypothesis was a speculative idea from the very beginning, statistically close to impossible. But when the team analyzed the metal content, the abundance of elements other than hydrogen and helium, in other old stars in the galaxy cluster, they found another anomaly. The oldest stars near the cluster's center had a significantly lower metal content than expected. This indicated they formed at a very early time in the universe, a time when stars had not yet begun to produce heavy elements. Normally, the center of a galaxy cluster should be the most metal-rich place, because generations of stars live and die there, enriching the space with heavy elements. But here, at the center, were primordial-looking stars that seemed to be from the first 200 million years of the universe. This completely contradicted standard models of galaxy formation. How could this be possible? Only one explanation remained. That region was different from the very beginning. If the supermassive black hole at the center began not from the collapse of stars, but as a giant primordial black hole, formed from a density fluctuation, right after the Big Bang, then the first stars and galaxies could have formed around it, around a pre-existing massive gravitational seed. This also aligned with the excessively massive early universe galaxies that Webb had found. It solved the problem of that black hole not having enough time to reach billions of solar masses, because it had started big. This had the effect of a bomb in the astronomy community. This was no longer a question about just one black hole, but about the origin of all supermassive black holes in the universe. Perhaps not all of them, but some were fossils as old as the universe itself. Webb's nearest instrument, the near-infrared imager and slitless spectrograph, can measure this polarization with incredible precision. The measurement was made, and the result was definitive. The polarization was rock solid, with less than a 0.1% change over months. This was impossible. An echo cannot behave like this. this meant only one thing. What we were seeing was not a mirage. It was a coherent, physically present structure. When this finding was published in the astrophysical journal Letters, it carried the headline, "The first direct evidence of a coherent structure in a black hole ergosphere." This ended decades of theoretical debate. The question was no longer, can structures exist in the ergosphere? The question had become, what exactly is this structure? How could this be possible? It suggested that the matter in that region was not just diffuse gas, but was somehow organized, perhaps held together by a complex dance of plasma and magnetic fields. Scientists were dumbfounded, because this was like nothing in the textbooks, and just when we thought we had seen the worst, the third epic moment arrived, the greatest cosmic fossil in history. The primordial black hole hypothesis was a speculative idea from the very beginning, statistically close to impossible. But when the team analyzed the metal content, the abundance of elements other than hydrogen and helium, in other old stars in the galaxy cluster, they found another anomaly. The oldest stars near the cluster's center had a significantly lower metal content than expected. This indicated they formed at a very early time in the universe, a time when stars had not yet begun to produce heavy elements. Normally, the center of a galaxy cluster should be the most metal-rich place, because generations of stars live and die there, enriching the space with heavy elements. But here, at the center, were primordial-looking stars that seemed to be from the first 200 million years of the universe. This completely contradicted standard models of galaxy formation. How could this be possible? Only one explanation remained. That region was different from the very beginning. If the supermassive black hole at the center began not from the collapse of stars, but as a giant primordial black hole, formed from a density fluctuation, right after the Big Bang, then the first stars and galaxies could have formed around it, around a pre-existing massive gravitational seed. This also aligned with the excessively massive early universe galaxies that Webb had found. It solved the problem of that black hole not having enough time to reach billions of solar masses, because it had started big. This had the effect of a bomb in the astronomy community. This was no longer a question about just one black hole, but about the origin of all supermassive black holes in the universe. Perhaps not all of them, but some were fossils as old as the universe itself. These three discoveries alone were a revolution. A structure where time slowed by 99%. Not a mirage, but a physical reality. And a cosmic fossil that could be as old as the universe itself. But the most incredible, the most unbelievable, the most impossible was saved for last. The fourth epic moment, the whisper of quantum gravity, that mysterious, unidentified spectral line. The team analyzed it for months. They compared it with all known elements, all plasma states, all possible combinations of temperature and density. Nothing fit. But then they tested a possibility proposed by some of the boldest theoretical physicists. What if that line wasn't from an atomic transition? What if it was something caused by the black hole itself? Or more precisely, by its spin? In a process called superradiance, certain types of particles can steal energy from the ergosphere of a spinning black hole. This process can cause the particles to form a massive cloud around the black hole. And this cloud eventually decays by emitting coherent radiation at a very specific frequency, just like a giant cosmic laser. This was a purely theoretical prediction. It had never been observed. But when the team calculated the frequency predicted by this theory and compared it to the energy of that mysterious spectral line observed by Webb. The result was chilling. The match was perfect, with 99.7% certainty. This could not be. This meant that not only general relativity, but also quantum field theory was being tested in the most extreme regime. This could be the first indirect evidence for the existence of a hypothetical particle called the axion. These particles had been proposed as a candidate for dark matter. How could this be possible? It meant that Webb might have observed not just a structure, but a structure created by a new fundamental particle. This was a discovery worthy of a Nobel Prize. It would fundamentally change not just our understanding of the universe, but our understanding of matter itself. The scientific world was literally split in two. Some argued it was a statistical coincidence. Others said we were entering a new era of physics, time dilation, a physical structure, a cosmic fossil, and now, the whisper of a new particle. All of this was coming from a single 0.6 billion light-years away. But when all these shocking discoveries came together, the resulting picture was even greater than its individual parts. It showed that the universe might have a hidden layer, not just strange, but far beyond our imagination. So what exactly is this layer? What does the sum of these findings tell us about the nature of the universe? And most importantly, what does this mean for humanity? Because, in the next step, we will examine the practical and philosophical consequences of these incredible findings. How they might forever change our thoughts about our place in the universe. Because, after this point, nothing. And so, nothing could ever be the same again. Because these discoveries are not just academic curiosities, they are sledgehammers, smashing our most fundamental assumptions about how the universe works. This is one of those moments that changes humanity's view of the cosmos, just like Copernicus removing the Earth from the center, just like Hubble showing the universe is expanding. Webb's findings show us that black holes are not just final destinations. They may also be the most creative and mysterious engines in the universe. Now let's look at the other previously unseen parts of this engine. The final epic moments that will plunge us into even deeper astonishment. The fifth epic moment, the rejection of a binary black hole system. One of the most plausible classical explanations was that there wasn't a single black hole at the center, but two supermassive black holes orbiting each other. This could be the remnant of a galaxy merger. Such a system could certainly create asymmetric lensing and strange infrared signatures. But to test this hypothesis, the team needed to work with incredible precision. Because if there were a binary system, there should be periodic variations in the signal due to their orbital motion. No such periodicity was detected during Webb's observation period. But that wasn't enough to disprove the hypothesis. Perhaps the orbital period lasted for years. So, the team resorted to a more subtle method, a dynamic analysis of the gas distribution at the cluster's center. A binary black hole system creates a very specific egg beater effect on the surrounding gas. It ejects gas at certain resonances and creates a distinct double-cored cavity at the center, typically a few parsecs wide. The team combined archival data from the ALMA telescope, the Atacama Large Millimeter Watch Submillimeter Array, with Webb's infrared maps. This was one of the highest resolution multi-wavelength analyses in history. When the results came in, everyone held their breath. The gas distribution did not show a double-cored structure. On the contrary, it was almost perfectly focused around a single, extremely dense central mass. This eliminated the possibility of a second supermassive black hole within a distance of 10,000 astronomical units, or AU, with 99.9% certainty. This was the almost certain death of the binary system hypothesis. How could this be possible? It meant that all that strangeness was originating from a single, or KE, ultramassive and ultra-fast spinning object. This did not simplify the problem. On the contrary, it made it even more mysterious. Because now there was no second object to share the blame. All the responsibility rested on the shoulders of that singular monster. And that brought us to the sixth, most unsettling epic moment, the discovery of magnetic field topology. The idea that plasma and magnetic fields played a role had always been there. But no one could have predicted how extreme a role they played. When the team examined the polarization data even more deeply, they mapped not only the stability of the signal, but also the polarization angle itself. This revealed the structure and direction of the magnetic field in that region. And what they found had never been seen in any black hole system before. The magnetic field lines were not just running parallel to the accretion disk as expected. They were twisted in an incredibly tight helix, like a DNA strand chucked around the black hole's axis of rotation. This helical magnetic field structure had been theoretically predicted in models like the Blandford-Znajek process, which explain how the rotational energy of black holes is used to launch particle jets. But to observe it so clearly and in a region so close to the event horizon was a first. The tightness of this helix indicated that the magnetic field strength exceeded 100 Gauss. This is 200 times stronger than Earth's magnetic field, and millions of times stronger than a normal galactic magnetic field. How could this be possible? It showed that the black hole's extreme spin was literally winding up and amplifying the magnetic field lines like a dynamo. This proved that the stable-looking structure was actually an incredibly energetic plasma, trapped and shaped by magnetic fields. This discovery was featured on the cover of Science magazine because it could be the key to solving a decades-old mystery of how black hole jets are formed. We now knew that the engine for jets was not just gravity, but magnetism twisted by gravity. This series of discoveries shook the scientific world repeatedly within a month. A place where time almost stopped, a structure that was not a mirage, a cosmic fossil, the whisper of a new particle, the collapse of the binary system, and now, a magnetic dynamo. Each one was a revolution on its own. But when all put together, the emerging picture was beyond imagination. It told us that not just that black hole, but perhaps all extremely spinning black holes in the universe host ecosystems far more complex, far more structured, and far more powerful than we thought. They were not just matter-devouring monsters. They were the universe's greatest sculptors, shaping matter, energy, magnetism, and even time itself. But now, it's time to slow down for a moment from this dizzying pace, to shake off the shock of these incredible discoveries. Take a step back and ask a deeper question. What does all of this mean? The slowing of time, the bending of light, cosmic fossils, and magnetic dynamos. What do these epic findings signify? Not just for a group of astronomers, but for every single person on Earth. Because, in the final act of this story, we will no longer talk just about physics and numbers. we will talk about humanity's place in this vast cosmos and the philosophical echoes of this new reality. Because what Webb has shown us is not just the depths of space, it is also the limits of our own understanding. And beyond those limits, perhaps the greatest discovery of all lies, the way the universe speaks to us and our capacity to listen. Because, from this point on, it's not just what we see that matters, but what we feel in the face of what we see and what we feel. And after this point, nothing can ever feel the same again. Because, when the bombardment of epic discoveries and dizzying numbers ends, all that remains is silence, and a single question echoing within that silence. What does all of this mean for us? Now is the time to stop and think, to slow down, take a breath, and in the light of this incredible knowledge, reevaluate our own place in the universe. Because, what Webb has shown us is not just distant galaxies and spinning black holes, it is also a mirror, reflecting the deepest and most poignant contradictions of what it means to be human. Let's confront the first contradiction, the state of being immeasurably large and tragically small. On one hand, there is an observable universe, 93 billion light-years wide. Within it, 2 trillion galaxies, each with hundreds of billions of stars, and as we now understand, probably supermassive black holes at the center of each. With event horizons larger than our solar system. On the other hand, there is you, standing on a tiny Archachuat's blue speck of dust in this vast cosmos, about 1.7 meters tall, with a life expectancy of roughly 80 years. The difference between these two scales is so unbelievably that our minds struggle to grasp it. This is our tragic truth. We will never be able to travel to that galaxy cluster, 6 billion light-years away. We will not witness the dance of light orbiting that black hole with our own eyes. We will not measure how time slows down on our own watches as we approach the event horizon. Physically, we are trapped in this universe. Our bodies are fragile machines, designed for the thin atmosphere and gentle gravity of this planet. Cosmic distances are insurmountable walls for us, and this can create a deep sense of sadness and insignificance in a person. But then you look at that image from Webb again, and you find an incredible beauty within that tragedy. Because, yes, we are physically small, but our minds are not. That 1.5 kilogram complex neural network inside our skulls is the only thing that can traverse that 93 billion light-year void. We cannot go to that black hole. But we can build a tool that makes its light come to us. We can design a gold-coated mirror to catch those photons at the end of their billion-year journey. We can analyze the subtlest frequency shifts in that light and conclude that time there is slowing down by 99%. You, too, are a part of this incredible mental leap. Your body might be sitting in this room, but your mind, right now, is wandering in the ergosphere of a black hole 6 billion light-years away. You are not just a passive receiver of this information. You are the very consciousness that gives it meaning, that feels it, that is left in awe by it. And this shows that being small is not a curse, but a privilege, because we are the part of the universe that observes, understands, heart, and appreciates itself. This is our power. This is our place. The second contradiction is about time, our being momentary witnesses to an infinite past. The universe is 13.8 billion years old. The light from the galaxy cluster we observed set out on its journey when multicellular life was just beginning on Earth. That black hole was already mature back then, had completed its spin, and may have been hosting the structure around it for billions of years. These are timescales the human mind cannot fathom. Our entire recorded history is a fraction of even the last second of that 6 billion year journey. This is our second tragic truth. We are merely transient spectators in this universal play, witnessing only the final act, perhaps even the final scene. We did not see how that black hole formed. We did not watch how it evolved over billions of years. And as we interpret this light, that structure may have already collapsed, dispersed, or transformed into something completely different. We can never see the universe as it is now. We are archaeologists of light, trying to piece together frozen moments of the past. This, on one hand, brings humanity's existential loneliness and transience to the fore. We exist for just a moment, and that moment is shorter than a blink of an eye on the cosmic calendar. But then you look again at that spectral line, that mysterious and narrow signature, and you realize the miracle hidden within that momentary existence. Because that moment is enough. Our 80-year lifespan is enough to unravel that 13.8 billion year history. Our knowledge accumulated over generations is enough to crack the code of that 6 billion year photon journey. We may be just the last word in the great book that tells the story of the universe. But that last word has the power to illuminate the meaning of all the sentences that came before it. We are the answers to the questions the universe asks itself. You, too, are part of that momentary but priceless testimony. You are the carrier of that miraculous consciousness that, at the end of 13.8 billion years of silence, can say, I understand. Your existence, no matter how short, is necessary for the universe to complete its own story. And this shows that being temporary is not a deficiency, but a gift that makes that moment even more precious. The third and perhaps most personal contradiction is this: being deeply connected in absolute solitude. Everywhere we turn our eyes, what we see is emptiness. The distances between stars, the darkness between galaxies. A journey to the nearest star system, Proxima Centauri. That takes 4.2 years even at the speed of light. This cluster is 6 billion light-years away. These numbers define our cosmic loneliness. We are like castaways on a single island of life in this vast ocean. This is our third tragic truth. The universe is indifferent to us. The black hole out there is not aware of your existence. Those photons did not set out on their journey specifically to reach you. They simply followed the path of least resistance, obeying the laws of physics. If Earth had not been on the path of those photons, they would have continued to travel through the void forever. This thought can make one feel like a coincidence in the universe, a meaningless accident. It is a deep sense of isolation. But then you look at the Webb project itself. You think of the thousands of scientists, engineers, and technicians who came together to build that telescope. These people, from different countries, different languages, different cultures, came together for a single purpose: to unlock the secrets of the universe. Think of the hands that polished those mirror segments, the brains that coded that complex software, the minds that designed that massive sun shield. They were connected to each other by invisible threads of shared curiosity, of a desire to understand, and that bond transcended the 6 billion light-year void. You, too, are part of this invisible bond. As you watch this documentary, As you read these words, as you think these thoughts, you are joining that global conversation. You are sharing the curiosity of those scientists. You are taking pride in the success of those engineers. And along with millions of people around the world, you are witnessing the same cosmic miracle at the same time. This is the antidote to loneliness. We may be physically separate, but in our quest for understanding, in our capacity for wonder, we are all deeply connected, and this gives us the greatest lesson of the universe. The greatest discoveries are made not when we reach the farthest distances, but when we are closest to each other. These three contradictions, large and small, infinite and momentary, alone and connected, form the philosophical landscape that Webb brings us. This landscape does not offer comforting answers. On the contrary, it prompts deeper, more personal questions. But the philosophical layers of this story do not end here, because, in the light of these discoveries, we are forced to rethink not only our place in the universe, but also the very nature of knowledge, what reality means, and most importantly, what our future as a species might be. Because what we see in the shadow of this black hole is not just starlight. Perhaps it is a reflection of our own future. And what we see in that reflection, is perhaps our greatest contradiction, finding creation within destruction. On one hand, we have a black hole, which we define as the most destructive force in the universe, a gravitational monster that tears apart stars, swallows planets, a beast from which not even light can escape. The event horizon is a point of no return. In the classic narrative, black holes are the junkyards of the universe. They erase complexity, destroy information, and reduce everything to a single, infinitely dense point, a singularity. This is our fourth tragic truth. It seems there is a mechanism at the very core of the universe that ends everything, that drags everything into meaninglessness. This gives rise to the thought that the precious complexity of life and consciousness will eventually meet a meaningless destruction. This is the feeling of the ultimate futility of existence, because no matter what we build, no matter what we learn, there is always a black hole that will eventually swallow everything. This thought can drive even the most optimistic souls to despair, but then you look again at Webb's data, at the hot structure glowing in that thin orbital band, at those helical magnetic fields, and you realize that this ultimate destroyer is also the universe's most creative sculptor. Because that black hole doesn't just destroy matter, it organizes it. With its extreme spin, it carves stable orbital pockets, or niches, in the fabric of space-time. With frame dragging, it winds up magnetic fields like a dynamo, generating the energy to fire jets that will span intergalactic distances. By slowing down time, it allows for chemical and physical processes to occur that we could never witness. This means that destruction and creation are two sides of the same coin. You, too, were born from this cosmic dance, because the carbon, oxygen, and iron atoms that make you up were forged inside a giant star billions of years ago. And that star at the end of its life destroyed itself in a supernova explosion, scattering these elements into space. Your existence is the result of a star's death, of destruction. Therefore, when you look at a black hole, don't just see an end, see a beginning as well. Because the universe constantly creates new order from destruction, new complexity from chaos, and we are both the product and the witness of this eternal cycle. This brings us to our final contradiction, perhaps the most hopeful one: discovering wisdom in our ignorance. At the very beginning of this journey, we thought black holes were simple, that they had no hair. Now, we understand that they host incredibly complex ecosystems, that their spin leaves indelible marks on the fabric of space-time. We learned that a region we thought was hidden is actually visible if you look with the right tools. An unidentified spectral line is whispering to us the existence of perhaps a new fundamental particle. This is our fifth tragic truth. The more we learn, the more we realize how little we actually know. Every answer gives birth to 10 new questions. As the horizon of knowledge expands, we see more clearly how vast the darkness beyond that horizon is. This can lead to an intellectual humility, even a sense of helplessness. The universe is so vast and complex that fully understanding it may never be possible. Our models will always be incomplete. Our theories will always be candidates for being shaken by the next impossible observation. This is a never-ending quest, and this quest has no end. But then you think of that first moment when Webb itself was born as an idea. Decades ago, a group of scientists asked, "What if we could look deeper? What if we could see a universe in the infrared that we've never seen before?" At the time, it was a dream. But that dream became a reality through the collective effort of thousands of people, with a $10 billion budget and decades of engineering. And now, that dream is fundamentally changing our understanding of the universe. This is the greatest beauty of knowledge itself, that it is not a destination, it is a journey. And the most valuable moments on that journey are not when we find the answers, but when we learn to ask better questions. You, just too, are a part of this endless journey. You carry the fire of curiosity inherited from your ancestors, and you will leave to the generations after you something far more valuable than answers. Better, deeper, yet bolder questions. Because wisdom is not knowing everything. Wisdom is having the courage to stand in awe of the vastness of what we do not know, and yet continue to ask. And this is the noblest definition of being human. In the light of these contradictions, we now see ourselves differently in the universe. We are tragically small, yet mentally limitless. We are momentary witnesses, yet we can read eternity in that moment. We are cosmically alone, yet deeply connected in our search for meaning. We find creation in the midst of destruction. And most importantly, as we understand the depth of our ignorance, we approach true wisdom. This journey began 6 billion light years away, in the heart of a galaxy cluster. But how, in reality, it ends within ourselves, in the deepest recesses of human consciousness, because the most important thing Webb has shown us is not how big or how old, or how strange the universe is. The most important thing Webb has shown us is how limitless our capacity to understand is. And this search within all this cosmic drama is the most hopeful message. Our journey is almost over. We have passed through dizzying discoveries, deep technical details, and philosophical reflections. We now know that even the shadow of a black hole, when looked at correctly, can whisper the secrets of the universe. We now know that the word impossible often means not yet measured. And we now know that our place in this vast universe is not to be an insignificant dot, but to be the consciousness that seeks the meaning of that dot. And this search itself is perhaps the greatest purpose of existence, because, in the end, only one truth remains, and that truth. In this journey, we saw how black holes bend space-time in incredible ways. But I didn't tell you something. This bending might also open a door to time itself. General relativity theoretically allows for paths into the past, so-called closed time-like curves. On our next journey, we will explore the physics of time travel. Can we really go to the past? Are you ready?